All right, so this is just going to be a midterm review for today. So we're just going to go over some of the logistics for the midterm, how best to study, and some sort of an overview of the concepts we've done so far, the most important concepts. We'll go over the formula sheet, some common questions I've been getting, and just some common sources of errors on this material. So okay, the first thing is the logistics of the exam. So as I mentioned before, we're going to be proctoring via Zoom since Respondus isn't available anymore on Canvas. So what that means, so we're going to have the exam during lecture time, so from 9 to 10:50 a.m. Now, you might see when you look at the exam on Canvas, I'm going to leave some buffer time at the end, so you might see that it's available until like 12 o'clock or 1 o'clock possibly. So it doesn't mean that you just have like 4 hours to take the exam, sometime during that 4 hours. That's just buffer time in case we run into some kind of Zoom issues or internet issues or whatever and we get a late start. So make sure that you sign on a little bit before 9 a.m. preferably, so that we can start right at 9 o'clock. Hopefully there'll be no issues. So make sure you check your Zoom setup beforehand, make sure it's updated, all the settings or whatever you need are all enabled, because you will need your camera working, obviously. So make sure that's all checked beforehand. Sign on, maybe 10-15 minutes before 9 o'clock. We'll start as promptly at 9 o'clock as we can, and then you'll have until 10:50 to take the exam. So as for the proctoring, you'll sign on to the Zoom meeting. The exam will be in the form of a Canvas quiz, just like the practice midterm is, similar in format, everything like that. So you'll sign on, you'll see the Canvas quiz. The Canvas quiz will open at 9 a.m. You can have a calculator with you, and you can print out the formula sheet if you want, or the formula sheet will also be available on the quiz itself. If you look at the practice exam, like the first thing that you see is the formula sheet on the top of the exam. So it will be available to you if you don't have like a printer or anything like that. Then the exam will consist of 4 to 5 multiple choice questions. So the multiple choice questions aren't intended to take a long time. They're not intended to be computationally intensive or even really require you to use your calculator. You should spend like 1 or 2 minutes on each multiple choice question max. They're sort of the kind of questions where it's like either you know it or you don't. And if you find yourself like going through a lot of calculations and spending a lot of time on a multiple choice question, that's not really the best strategy since they're only worth 5 points each. You don't want to spend too much time on the multiple choice. And then for the multiple choice, obviously there'll be no partial credit since either you get it right or you get it wrong. So there'll be no partial credit considered for the multiple choice. But then for the short answer, there will be partial credit. So there'll be 3 or 4 short answer questions depending on how many parts they have. You will get partial credit for that. So you'll have, bring like some empty paper with you to the exam. You'll be able to write out all your work. And then at the end, you'll upload it. So now for the short answer, you have to enter in your final answer that you have on your work. Enter that into the box that is available on Canvas. So you'll see, just like in the practice exam, after each short answer question, there's a box where you can enter in text. So now to enter in your answers on Canvas, it doesn't have to be like a fancy formula or anything. So for example, for one of the questions you have for part A, you get like 47, newtons per coulomb or something. You can just enter in like, just type A 47, just so that it's clear that the work that you're submitting after the exam is the same work that you did during the exam when you had the Canvas quiz in front of you. Likewise, if there's like a formula or something like that, you can just type out, let's say it asks for the electric field of something. You can just type out like sigma over epsilon, like sub-zero. You don't have to like go into the insert formula and look for all the Greek letters and stuff like that. You can just write something like this and that's totally fine. So I'm also going to give you like an extra 15 minutes at the end to enter in your answers, so you don't have to worry about that taking time away from your actual exam time. There will be the hour and 50 minutes for the exam, and then there'll be an additional 15 minutes to enter in all of these answers, just so that there's a buffer there as well. So just enter in all of your final answers. If you didn't finish a question, and let's say you only got up to like halfway through the question, and you just have like a formula, you can just sort of enter in like a rough, description of that formula here, basically. So it doesn't have to be perfect, just something so that it's clear that you're submitting the same work. But it is very important that you do enter in, your answers. If you submit basically like a blank Canvas quiz and then upload your work later, we're not going to grade that. So you need to enter in your answers for every question that you have answered on your paper as well. Otherwise, it won't be graded. And then when you're done with your exam, just upload your work. So either take a picture or scan, whatever is easiest for you. Just upload your work. There'll be a assignment titled Midterm Work that you'll see in assignments. So just then upload, a PDF or a JPEG of your work, and that is what we will grade for the partial credit. And then once you're done doing that, once your work has been uploaded, then disconnect from the Zoom meeting, and then you're done. Okay, so just to recap, sign on to the Zoom meeting. It'll be titled like Midterm. You'll see it in the Zoom tab on Canvas. Sign on a couple minutes early. We'll start at 9 o'clock. You'll have an hour and 50 minutes for the exam. You'll have an additional 15-minute buffer time to enter in those answers. When you're done with your work, make sure that you have circled your answers clearly on your paper, and that you've also entered those answers into the boxes on Canvas, and that they match up to a reasonable degree. And then once you're done with that, upload your work, submit it on Canvas, and then you're all done, and you can sign off. So if you have any questions about how the procedure of this will work, obviously don't hesitate to ask me. I'd rather get any questions squared away before the exam than have some kind of confusion or misunderstanding during the exam. So don't hesitate to ask anything or come to my office hours if you have any questions about this procedure. Okay, then just a couple of other tips and how the exam will be graded. The number one thing, obviously, is to write neatly. So that's the most important thing you can do. Now, I know obviously, on an exam, you're like under time pressure. I know it's hard to like keep your paper neat and orderly, but to the best of your abilities, write as neatly as you can. The neater you write and the clearer your work is, the more partial credit we can give you if we can clearly see where you made a mistake, or if it was just like some careless little error. So it's in your best interest, obviously, to write as neatly as possible. So that being said, so when we're grading, if I don't take off credit for like a visible careless error, but that also depends on how clearly your work is written. So if, let's say, you write something, you write down like Coulombs Law, and let's say you write this down, and then you write, okay, like I've got K, and then you have some number for Q1, and you write down some number for Q2, and then you write some number down for the distance there, but then you forget to write that squared here. If your work is very clear, where I can clearly see that you wrote down like R squared here, but then just forgot to square it in your calculator, that's not something that's going to lose you any points. But like I said, that's contingent on your work being very clear, where if we can clearly see that that's what your error was, and that was your only error with that, we won't take off points for that. However, if it's not clear where the numbers came from, or it's not clear what formula you're using, then we just take off points, however many points is reasonable. So it's definitely in your best interest to write as neatly as you can and sort of write out all of your formulas, write out what numbers you're plugging in. That will get you the most partial credit. And we also do our best, let's say if it's a multi-part question and you make a mistake in part A, we do our best not to penalize you multiple times for the same mistake, but again, that's contingent on how clear your work is, and how clear it is to us that you did everything else right, besides that one little mistake. But we want to give you as many points as we can, so the neater and more clearly you show us your thought process, the more points we can give you for partial credit. Now, another thing that can get you partial credit is recognizing if your answer is wrong. So let's say we have a problem where it's like an infinite cylinder and you have to use Gaussians Law to find the electric field somewhere. So let's say you know that the electric field for an infinite cylinder is given by this. But when you do Gauss's law, you make a mistake somewhere, and you end up with something that's like, some constants, then you get like r squared. And you say like, okay, that's clearly wrong. I know it should have a 1 over r, and I'm getting an r squared, so I clearly made a mistake somewhere. If you just write like, 1 or 2 sentences on your paper saying like, I know this is wrong because the electric field for an infinite cylinder should look like 1 over r, and mine looks like r squared, so it's clearly wrong. That will get you back some points because you recognize that you made a mistake. You know what your answer should look like. So that will get you back, at least a point or two, recognizing that you made a mistake somewhere and that your answer is not consistent with, what we know. Okay, so now I want to just go over the formula sheet. Okay, so this is the formula sheet that you'll have on the exam. Now, you'll notice that the majority of the equations are from chapters 24, 25, and 26. And that's because chapters 21, 22, and 23, like I said, are sort of the most important chapters that we've done so far. They're really like the foundational, it's the foundational material for electromagnetism. So Coulombs Law is not on here, so that's something that I expect you to memorize. Gauss's law is not on here. That's something you should memorize. The potential for a point charge, the electric field for a point charge, those are the kind of things that you should memorize for the class. Now, I know that it might sound counterintuitive, but the reason that I don't put a lot of those foundational formulas on the formula sheet is A, I want to force you to memorize them, and B, students actually do worse with a formula sheet. So, I've graded like thousands of exams, and there is a noticeable difference between when there's a formula sheet and when there's not. So, like I said, even though it sounds counterintuitive, when you're given a formula sheet, it's very easy to sort of like treat it like a safety blanket almost and not study as much as you should. I've been guilty of that when I was a student as well. You think, oh, I have all the formulas, therefore I don't have to spend any time studying those formulas. And then what ends up happening is like you sort of then don't know what the formulas actually do or what they mean or what the variables in the formulas are for. And students end up kind of just like writing down random formulas from the formula sheet, and it's clear that they don't really know how to apply the formula. Whereas if you force students to basically memorize the formulas, they very clearly have a better understanding of how to apply the formulas and when to apply what formulas. So I'm really doing it, for your own good. You will actually learn the material better without having these formulas available. So I'm not just trying to, be mean. It really does make a difference in how students perform on the exams. So that being said, it is very important to actually study your formula sheet. Like I said, a trap that is very easy to fall into is you say, okay, I have these formulas on the exam, therefore I don't have to study them. But then what happens is on the exam, you're like, I don't know what any of these letters mean, I don't know when what formula is applicable, and it ends up hurting you. So let's go over the formula sheet. We'll go over all these formulas so that we know when all these formulas are applicable and what they're for. Okay, so first up here we have some of the formulas from like chapter 24 in capacitors and dipoles. So this is the formula for the torque on an electric dipole, where tau is the torque on your dipole, P is that dipole moment, where P is it's right there, JK, where P is equal to QD. So these two formulas go together, and well, actually, all the top three do. So the top three formulas, that's the same P in all of them. So you have your torque, you have your actual dipole moment then, where P is the dipole moment here. So this is your dipole moment. Q is the magnitude of the charges. Remember, a dipole is a positive and a negative charge of equal and opposite sign. So you just have like plus Q and minus Q. So you just have that magnitude charge here. And then you have the distance from your negative to your positive charge. And this vector points from the negative to the positive charge. So this P and this P are the same. And then also it's the same P here. So this is the potential energy of a dipole. So these three equations go together. So this is all dipoles. Now, the next couple equations are all for capacitors. So this is mostly from chapter 24. So I'll circle these here. So then we have our capacitor equations. So these are for capacitors. So this is just the equation for capacitance. It's just the charge on your capacitors divided by the potential difference between them. And this potential difference will be E times D. So that is not a formula that's on your formula sheet. The potential difference between the plates of your capacitor is given by the electric field between those plates times the distance between the two plates. So this is your capacitance. Then here we have just the formulas for capacitance in series and parallel. So this is kind of self-explanatory here. And then this is potential energy for a capacitor. So all three of these equations are equivalent to each other. It just depends, do you have the charge in the capacitance, or do you have the capacitance in the voltage, etc. So these are all equivalent, but it's very important to remember here, this is what I mean by you have to study your formula sheet. We have two equations already for capital U. We have U is equal to negative P dot E, and U is equal to all of these things. So it's very important to understand that this is the potential energy for a dipole in an external electric field, and this is the potential energy for a capacitor. And then here, this lowercase u is just the energy density in your capacitor. So this is just equal to capital U divided by the volume between your plates. Okay, and then we have some current and circuits. So this section is current and circuits. So here we have the current, which is given by the number density of your particles times the charge on those particles, the magnitude, the drift velocity, and then the area, the cross-sectional area of your wire. Remember, current is not a vector, it's a scalar, even though we do draw it with a direction, it's not technically a vector. And then J is our current density. So J is basically just I divided by the area. So J is equal to the current divided by the area, which gives us the current density. And now also it's important to note that J is a vector, but that won't be too important for us until we get to magnetism. Then we have the electric field is related to the current density by the resistivity. That's rho. Then we have the resistance is related to the length and the area of our wire. So this rho and this rho are the same. That's the resistivity of our metal. It's material dependent, so different materials will have different resistivity. All right, and then here we get sort of more into circuits. So this top portion was sort of current, and then this bottom portion was more for circuits. So right here we have Ohm's law. So this is one of the very important laws that we should sort of memorize. So V equals IR. V is the potential drop over some circuit element, usually like a resistor. I is the current through that element, and then R is the resistance of that resistor. And then this equation is for when we're looking at the potential over like an imperfect battery. This little lowercase r is the internal resistance for a battery. But in many cases, we're just going to be looking at an ideal battery, which means that that little R is 0, which means that the voltage across your battery, between the terminals of your battery, is just equal to the EMF supplied by that battery. Okay, and then this is just the power dissipated by some circuit element, typically a resistor. And again, all three of these are equivalent. It just matters, do you have the current and the potential, or the current and the resistance, but they're all equivalent. Okay, and then up here, you have your resistors, equivalent resistors in series and parallel. Then here we get into, this is from chapter 26, we have charging a capacitor and discharging a capacitor. Remember, for these, the lowercase q and the lowercase I means that it's time dependent. So this q is really, remember, they're really functions of t. So this is really functions of t here. And the same for discharging a capacitor. The lowercase q and I is a function of time, so both of these are technically functions. Now, as I mentioned before, the exam will cover chapters 21 through 26, but the most important chapters are 21, 22, and 23. So if you're crunched for time, it would definitely make sense to focus most on chapters 21, 22, and 23, and then go on to chapters 24 and 25, and then last go on to chapter 26. All right, now let's just go over some of the general formulas that are most important that are not on the formula sheet that you should memorize. So first and foremost is Coulombs Law. So Coulombs Law, remember, it's the force between two particles. You have Q1 and Q2. It's over 4 pi epsilon naught, and then r squared, where r is the distance between them. So it's very important to remember that Coulombs law only applies to point particles or spheres, since spheres act like point particles once you're outside the sphere. So this is for point particles only. So if you have like two line charges, or like two infinite line charges, or a disk and a ring, if you have anything that's not a point charge, Coulombs law will no longer apply. You would have to modify it quite a bit. So this only applies for point particles, and you need two of them. So remember, Coulombs law, since it's a force, in order for a force to be present, you need two things. So for Coulombs law, you need 2 point particles in order for there to be a force. Now this is in contrast to the electric field, where the electric field is only due to a single charge, or a single distribution of charge, like a disk or a ring. So the electric field for a point charge is also a vector. And again, this is a point charge, a single point charge. And again, the 1 over r squared dependence of Coulombs law and the electric field is very, very important. That's like one of the defining features of electromagnetism, is that we have this 1 over r squared force and this 1 over r squared electric field. Now we also have a related equation. We have this. So we have F equals Q times E. Now this equation is always true. So these two equations were sort of true in specific situations. If we have a point particle, if we have 2 point particles, this equation is true for any electric field where this Q is a point particle. So this equation will give you the force on some point particle due to any type of electric field. So whether it's the electric field due to an infinite sheet, or an infinite line, or it's just some arbitrary electric field that you were given, if you're trying to find the force on a point particle in that electric field, this equation will always hold. But this charge here does need to be a point particle. Now, there are very similar equations for electric potential and electric potential energy. So the electric potential energy associated with a pair of charges, a pair of point charges, looks almost exactly the same as Coulombs law, except it's a scalar, right? There's no vector quantities here, and I have only 1 over r in the denominator, so there's no r squared here. So this is the potential energy between 2 point particles. So really the only difference between our potential energy and our Coulombs law formula is that we have 1 less power of r in the bottom, and it's not a vector, it's a scalar function. Okay, then we have the potential of a point particle. So V is equal to Q 4 pi epsilon naught r. So again, this is very similar to our equation for the electric field, except we have only a single power of r in the bottom, and it's a scalar function. There's no vector here. So this is the electric potential for a point particle. And again, it's very important to remember this is only for a point particle. As I said before, if you're looking at the potential for a capacitor, the potential for a capacitor is given by the electric field between the plates times the distance. So even though both are represented by V, they have totally different forms, and they're applicable in completely different situations. So this is the potential for a single point particle. Just like the electric field, the potential is associated with a single particle or a single charge distribution, like the potential for a ring or a disk or an infinite line. You don't need pairs of charges to make sense of potential. It is associated with a single charge distribution, whereas the potential energy, you need multiple charges, you need pairs of charges in order for potential energy to make sense. And then we also have another similar formula to what we have here. We have the potential energy of a point particle in some arbitrary potential. So again, this is a point particle here. And this is any potential. So it doesn't have to be the potential created by another point particle. It could be the potential created by a capacitor. It could be the potential created by an infinite line. It could be any potential. This equation will always hold. So if you're looking for the potential energy of a point charge in some arbitrary electric potential, this equation is how you do it. Okay, now let's go on to Gauss's law. So Gauss's law is super important. There will definitely be a Gauss's law question on the exam, so absolutely make sure you know how to use Gauss's law. So Gauss's law is this. So Gauss's law is the surface integral of the electric field over some arbitrary surface, closed surface. And that is equal to the flux, which is equal to the enclosed charge in that surface divided by epsilon naught. Now, it's important to remember, as I mentioned in our lecture on Gauss's law, it's important to remember that Gauss's law is always true for the electric field. It's just not always useful to us. So when we do problems with Gauss's law, we want to use it on problems that have a very high degree of symmetry, where this integral becomes very simple. Because if we don't have a high degree of symmetry, this dot product might introduce a cosine theta that we have to integrate over, or this electric field might be very complicated where it's almost impossible to integrate over it. So we want to choose only specific scenarios where this integral becomes very easy, where we basically aren't even really integrating. So those situations, there's three scenarios where you want to use Gauss's law, or where Gauss's law is useful. And that's when you have spherical symmetry. So in cases where you have spherical symmetry, that's like if you have concentric shells, or you have an insulating sphere with a uniform charge distribution, anything that's spherical in nature, a point charge, anything. So in this case, you'll have E dot dA is Q enclosed over epsilon naught. So in the case of spherical symmetry, your dA here will be 4 pi r squared. It's going to be the surface area of a sphere, since when we're doing Gauss's law in spherical symmetry, we want to choose a sphere to integrate over. So this is the surface area of a sphere. This is something you should also memorize. Memorizing the surface area of a sphere, the volume of a sphere, things like that are all very important. All right, then the other case is cylindrical symmetry. So symmetry. So that's like if you have an infinite line charge, an infinite cylinder, concentric infinite cylinders, those all have cylindrical symmetry. So you're going to want to choose a cylinder for your Gaussian surface. So in this case, Gauss's law will still be E dot dA, obviously. But for your dA, you're going to want to choose a cylinder. And that will be 2 pi RL. Now, in this case, since let's say if we have an infinite line charge, the only portion of our cylinder, our Gaussian cylinder, that will contribute to this integral is sort of the side. It's this outside portion here. So that's why we're plugging in 2 pi RL, because 2 pi RL is just that side portion of our cylinder. So when we do a Gaussian cylinder like this, sort of like the caps of our cylinder over here and over here, those don't contribute to our integral because the dot product between E and dA is 0. So the only part that contributes in this case is that 2 pi RL of the side of our cylinder. So this is where most people, most students basically lose points when they're doing Gauss's law problems, is basically just not knowing these area formulas here. So it's really important when you're doing Gauss's law, remember for your spherical symmetry, your surface area of a sphere is 4 pi r squared, and your surface area of that side of the cylinder is 2 pi RL. It's the circumference of the circle times the length will give you the surface area. So those are the main mistakes, definitely the most common by far mistake that students make with Gauss's law. And then the other case where we use Gauss's law is when we have plane symmetry. Now, this one is kind of easy though, because there's really not too much to do with a plane. It's just you have a plane with a surface charge, and there's really only one way to do that. So we have E dot dA is Q enclosed over epsilon naught. Now, if you look back at our notes when we did Gauss's law to solve for the electric field of a infinite plane, we saw that the area didn't really matter, like what shape it was, because it canceled out on both sides. It canceled out on this side of the equation, and it canceled out over here. So for plane symmetry, we don't really have to worry about like the formula for A here, because it can be any area, any shaped area, since it cancels out on both sides. But the important thing to remember here is just what the answer ends up being, basically. So we'll do that now. So let's go over the most important electric fields for each of these cases. So for spherical symmetry, obviously the most important thing is the electric field of a point charge, which we already did. So I'll write that over here. So the electric field for a point charge is just given by this. And this is outside your sphere. So your electric field outside a sphere or the electric field of a point charge are the same, and it's given by this, where Q is the total charge of your point or your sphere. Then cylindrical symmetry, the electric field of a infinite line charge is given by this. So the electric field of both an infinite line charge and the electric field outside an infinite cylinder will look like this, depending obviously on what your lambda is, if it's positive or negative. If you have like concentric cylinders, they might cancel out to give you 0 electric field outside, maybe. So this is what the electric field would look like for either an infinite line or once you're outside a single infinite cylinder. And then the electric field for an infinite plane is just E is equal to sigma over 2 epsilon naught, and the direction is just like away from the plane. If this sigma is positive, and if it's negative, then it just points towards the plane. But the general formula is sigma over 2 pi epsilon naught. And so like I said, there will definitely be a Gauss's law problem on the exam, so make sure, in addition to sort of just like knowing the general form of each electric field, make sure that you know how to use Gauss's law to get to each one. So make sure you do a lot of problems of Gauss's law with spherical symmetry, maybe the concentric shell problems we did. I think we did one in discussion and one in lecture where we had like concentric shells and we used Gauss's law at different sort of locations within the shells and found the electric field in each portion. So that's a really good type of problem to know how to do. Cylindrical symmetry, we also did a couple of those in lecture and discussion. So make sure you know how to apply Gauss's law to these various cylindrical situations. Know how to get to here from an infinite line charge. Sort of know how to handle it if you have coaxial cylinders. We did one in lecture where we had two coaxial cylinders where one was plus lambda, one was minus lambda. So make sure you know how to do that. And then for the infinite plane, there's really only one type of infinite plane, so there's not too much to study with that. If you just study the infinite plane, then you pretty much know every problem with infinite planes. So, like I said, the good thing about Gauss's law is that you can only use it in these three scenarios. You can only use it when there's spherical symmetry, cylindrical symmetry, or plane symmetry. There's no other type of scenario where you're going to be asked to use Gauss's law on an exam. So if you just study a couple problems and know how to apply it in each of these three cases, and really only just the top two, because the plane symmetry, there's only one infinite plane. So there's not really too many variations of the plane symmetry. So really your spherical symmetry and your cylindrical symmetry are the ones that you might see, like I said, coaxial cylinders or concentric shells, or an insulated sphere. We did one problem with the insulated sphere. Okay, so those are the main takeaways from Gauss's law. Now let's move on to electric potential. So electric potential is our other big topic. So there are two ways to solve for electric potential. We saw this way, where we can integrate over the charge distribution, or we can integrate from some reference point to whatever point we're measuring the potential at, and we integrate the electric field. So these are the two ways you can calculate potential. Now, you would use this form. You would integrate over the charge distribution if it's a finite charge distribution. So for example, like a ring or a disk, one where the electric field isn't immediately knowable. When we solve for the electric field for a disk or a ring or a finite line, they were very ugly formulas. So you wouldn't want to integrate over that to then find the electric potential. That would be a very cumbersome way to solve the problem. So if you have a finite charge distribution where the electric field is not something simple to integrate over, you're going to just want to integrate over the charge distribution. Now, it's very important that it's a finite charge distribution. You wouldn't want to use this in the case of an infinite line or an infinite cylinder, because then you'd have to integrate from infinity to infinity and your integral wouldn't converge. So that integral wouldn't make any sense. So only use this if you're dealing with a finite charge distribution. And the three main cases we saw the disk, we saw a ring, and we saw a finite line. So those are really your three main cases where you would integrate over the charge distribution to find the electric potential. Now, the other method where you integrate over the electric field to find the potential, this you would want to use if the electric field is easy to solve for, basically. So in problems where you can use Gauss's law, and you can easily find the electric field, that's when you'd want to use this, or where the electric field is very simple. So like in the case of a sphere, some sort of sphere, you know the electric field outside a sphere, a charged sphere, right? You know it's q over 4 pi epsilon naught r squared, and that's an easy function to integrate over. You just integrate 1 over r squared, and that's really it. So that would be like a good case where you want to just integrate over your electric field. So something where you can apply Gauss's law, quickly find the electric field. The electric field is relatively easy to integrate over. That would be a good candidate for this method. Another thing that you would want to, or another time that you would want to use this method is when you have an infinite charge distribution. So if you have an infinite line, an infinite cylinder, that would be when you would want to integrate over the electric field, because you can't use this method. As I said, it would give you a nonsensical answer. And you can also quickly and easily find the electric field of an infinite line or an infinite cylinder by just applying Gauss's law. And then your integral would be very easy to solve. You would just have a 1 over r basically, and that would just give you that natural logarithm. Okay, and then some common potentials. So as I said before, we have the potential of a point charge. So this is a point charge, or a charged sphere when you're outside that sphere. Then the other one that we use the most is the electric field in between the plates of a capacitor. So this is for a capacitor, where d is the distance between those plates. And those are really our two most common potentials that we use. Now, another thing about potential, remember I said that just because the electric field is 0, that does not imply that the potential is 0. So what that does imply is that the potential is a constant. So remember, if E is 0, that means that the potential is a constant. So for example, if you're inside a conducting sphere, so if we have a conducting sphere, let's say a solid conducting sphere, so we have a solid conducting sphere with a charge Q sitting on the surface. The potential V will be equal to 4 pi epsilon naught r outside, and then V will be equal to a constant inside. And now the constant will be the value of the potential at the surface. Now I know that you can figure that out two ways. One way is that you can do this integral. You'll integrate from infinity to the radius of your sphere, capital R here, and then you'll integrate from capital R to some point inside your sphere. And we did this in lecture. Or the other way you could know it is you don't have to integrate at all, and you can just say, well, I know my potential is continuous. And if my potential is continuous, and I know that it's constant inside the sphere, then whatever value it is at the surface, it has to be that same value all the way through the sphere. Because if it's constant and continuous, it can't be anything else. So if I was to plot, the potential for this solid conducting sphere, or even a conducting shell, it would look like this. So it would sort of go like 1 over r out here, and then it would be a constant here, where this is r. Capital R, the radius of the sphere. And now if I were to plot the electric field in this case, so let's say I plotted the electric field for my conducting sphere with some charge, it would look like this. It would be 0 inside the sphere, and then it would sort of jump up, and then it would decrease with 1 over r squared. And the electric field now would have some discontinuity. So you can see here that the electric field has a big discontinuity at the surface of your conductor, whereas the potential is continuous, right? This is a continuous function. There's no discontinuities, there's no jumps. So your potential is always continuous everywhere. Your electric field will have a discontinuity at the surface of a charged conductor. Okay, and then I just want to quickly go over the types of problems you're likely to see from chapters 25 and 26. So if you look at the practice exam, the question that deals with the material from chapter 25 and 26, like the circuit question, was very similar to these examples here. So this is from chapter 26, part 1. So these examples where you have some circuit with a combination of capacitors in parallel and in series, and then it asks you find the equivalent capacitance, find the charge on one of the capacitors, find the voltage across one of the capacitors. That was the question that was asked in the previous summer session, very similar to this one here. So that's like one of the likely types of problems that you might see on the midterm. So let's just copy this and let's just recap this a little bit. So for these types of problems, these two capacitors are in parallel, and this one is in series with these two. So you can write this as a circuit like this. This is the battery. So we'll call this C12, and this is C3. And then likewise, you can rewrite this circuit again as an equivalent capacitance, this is the voltage, of all three of those capacitors. So always start with capacitors in parallel when you're changing them into equivalent capacitance. You always want to do the ones in parallel first, because if you try to find the equivalent capacitance of C3 and C1 here, you wouldn't be able to do it. You would need to find the equivalent capacitance of these two in parallel first, and then you can do the ones in series. So for capacitors, let's do the ones in parallel first. So we already saw on the formula sheet, we know how to add capacitors in series and parallel. But when we're talking about the charge and the voltage on capacitors in parallel, we sort of have to think a little bit more conceptually. So in parallel, the voltage across, in this case, C1 and C2 will be the same. So in this case, V1 will be equal to V2, and this goes for any number of capacitors in parallel. If you had like 10 capacitors all in parallel, the voltage across each one would be the same. And that's because we know that potential difference is independent of your path taken, right? We said the electrostatic force is conservative, therefore it's independent of path. So we know that the potential difference only depends on the endpoints. So that means no matter how you get from A to B, right? So whether you go over capacitor 1 or you go over capacitor 2, the voltage difference, the potential difference has to be the same. So when you have capacitors in parallel, the voltage across them will be the same, but the charge will not be the same. So Q1 will not be the same as Q2. You would have to use your equation for capacitance, so you'd have to use this equation to figure out the charge on each of those individual capacitors. Now, when we have capacitors in series, now the potential is not the same across each one. So the potential, so we'll call that V total, will be equal to the sum of the potential across each capacitor. So if we have 5 capacitors in series, the sum of the potential difference across each one will be equal to our total voltage drop across the whole circuit. So in this case, if this was, let's say, 10 volts here, so we were told we had a 10 volt battery or something, the sum of this capacitor and this capacitor, the voltage drop across each of these would be equal to 10. So this might be like 8, and this might be 2, or it might be, it could be 5 and 5, it could be 6 and 4, but the sum would be equal to the total voltage drop. And this is true even though here C12 is an equivalent capacitance of 2 capacitors in parallel. So then we also have the charge on capacitors in series. So capacitors in series do have the same charge on them. And this is true no matter how many capacitors you have. If you have 5 capacitors in a row, all 5 of them will have the same charge. So when you have problems like this, where you have some combination of capacitors and it asks for, like the charge on one of them or the potential difference on one of them, what you want to do is you first want to find, condense your circuit down so that you just have one equivalent capacitance. So you want to kind of condense it down to here. And then what you're going to do is work backwards through sort of each step. So each step you did to condense it down, you're going to work backwards across each one now, applying these rules at each step until you get to whatever capacitor it is you're looking at. So we did this problem in lecture, so definitely make sure you go over that and understand sort of how I worked backwards to find the charge on the capacitors. There's one on the practice exam, so definitely practice that one, and I think you also did one in discussion. So you have a couple of problems to choose from to practice that. Then the other type of chapter 25-26 question that you could get is a basic Kirchhoffs Law problem. So I won't ask anything like this where we did that one problem where we had like a bunch of different equations and took like a whole page of tedious algebra to solve for the different currents and stuff. I wouldn't ask you something like that on an exam. That's way too time consuming and it would be way too hard to grade also. So something very straightforward. So I wouldn't ask you anything like this circuit, but maybe a straightforward, let's see if I have any examples here. So it would be something more like this, where you just have like maybe one loop or like two simple loops and just a single battery. I won't ask anything with multiple batteries. It will just be one or two loops with a couple of resistors and like one battery. So the important thing for these problems is basically just to remember these sign conventions. So I know it's a little bit tedious, but if you sort of think about it physically, it's not that bad. So when you're doing Kirchhoffs Law and you're traveling from the negative to the positive terminal of your battery, that's the way current wants to flow. Current wants to flow out of the positive terminal, go around your circuit, and go back into the negative terminal, and then keep going around that way. So since batteries supply a potential difference, it makes sense that when we're using Kirchhoffs Law, if we travel from the negative to the positive terminal of our battery, that would give us a positive EMF, right? Because we're supplying power via the battery to our circuit. So that's like the physical interpretation of this sign convention. And then if you're going in the other direction, so if you're going from the positive to the negative terminal, so how I remember it is I just remember that this is the direction that physically makes sense to me. So if I'm traveling the opposite direction, I just add a negative sign and I have a negative EMF. So sort of remember, like, this is the base case, and if you're traveling opposite to that, you just pick up a negative sign in front of it. And then the same thing for when you're traveling over a resistor. If you're traveling in the direction of your current, so in this case, you're traveling in the same direction as your current, when you go over a resistor, you lose energy. Just like in a toaster, when you pass current through the resistors in your toaster that make up like the hot thing in the toaster, you're clearly losing energy there. So resistors dissipate energy. So when you're traveling in the same direction as your current, your resistor is going to want to like dissipate that energy out into the world. So you're going to have a minus IR because you're losing energy from your circuit. So this is like the base case I think of for here. So I think of these two cases are my base cases that physically I can intuitively understand why those have the signs that they do. So if I'm traveling in the opposite direction of my current, I just add in an extra negative sign, which will give me plus IR. So these are sort of the two most important things to understand because those are like the physical, intuitive cases. And then if you're like doing the opposite as you do Kirchhoffs Law, you just add an extra negative sign. And remember, all Kirchhoff's rules come down to is conservation of charge and conservation of energy. So we know that the electric potential is going to be 0 around a closed loop. So as we go around our circuit and we apply all of our rules to the resistors and the batteries, we want all of that to add up to 0 because we know that the potential around a closed loop has to be 0. So that's where this law comes from, or rule. And then similarly for the current we can think of as charge. So this is just conservation of charge. So the current in, the charge into some junction has to be the charge out or the current out. So however many electrons you have flowing in here, you have to have the same amount of electrons flowing out. So that's all these two rules are telling you. It's just conservation of energy and conservation of charge. Okay, and then there's just one other thing I just want to mention just in general. I noticed in the previous summer session, I asked a question that said find something as a function of time, as a function of t. And not everybody knew what that meant. So since that's a term that you'll see a lot if you take physics or engineering, I just want to clarify that. So a function of time just means some function where your variable is t. So that might be like 5t squared plus 2t, or it might be like e to the t over rc, negative t over rc, that's a function of t. So that's all it means. It just means some function where your variable is the time t. It does not mean, I saw a lot of people actually solved for the time. So they like sort of wrote something like this and then solved for t. That's not what a function of time means. A function of time just means your variable, write some function where the variable is t. Okay, so that is really it for the review. That was all the main things I wanted to cover. Again, feel free to email me if you have any questions. So the main things to keep in mind, there will definitely be some kind of Coulombs Law problem where you have to find the force between particles. There will definitely be a Gaussians Law problem for sure. And there'll definitely be some problem that includes electric potential, whether it's calculating the potential or something with conservation of energy. And then like one short problem on circuits, either find the charge on this capacitor or find the voltage across this capacitor, or a simple application of Kirchhoffs rules. And that will be pretty much the exam. Okay, so I hope that gives a somewhat comprehensive overview of all of our topics. Again, don't hesitate to email me if you have any questions, and I will see you guys on Monday.